In this lecture, we will talk about decomposition of strain tensor. It is very important to understand the decomposition of stress or strain tensor in order to understand the theories of failure. So stress tensor or strain tensor both can be decomposed into hydrostatic and deviatoric components. The hydrostatic component of stress it results in change in volume, whereas deviatoric component of stress results in change in shape. So basically there are two major deformation modes. One is change in shape, other is change in volume. So let's talk about first the decomposition of strain tensor epsilon ij. So this is our strain tensor. As we know, all 9 components of strains. Now let's decompose it into these two matrices. Okay, let's say this is matrix 1 and matrix 2. So what I did here, the diagonal components we have kept it in matrix 1 and off diagonal components are in matrix 2. So now these two components, the objective here is that we want to split the strain tensor epsilon ij into uh, two pure hydrostatic and pure deviatoric strain tensor. So this M1, okay, the question is whether M1 and M2. So whether M1 is pure hydrostatic and whether M2 represents pure deviatoric component of strains. So let's see that. So let's see first matrix 1. So epsilon 1 1 2 2 and epsilon 3 3, these three diagonal components. Let's see what is epsilon 1 1. If we are given just no, the strain state, which is epsilon 1 1, and all other components are 0. So epsilon 1 1 looks the deformation something like this. Okay, whereas this cube, let's take the very simple cube structure or infinitesimal volume element. Let's take it is of the shape cube, and epsilon 1 1, if we say it looks something like this. The this face just deforms by some magnitude only in x direction. So this is epsilon 1 1, and similarly epsilon 2 2, this face deforms in a y direction. This is x, y and z. So this phase moves in y direction. So this is epsilon 2 2. So this is pure strain in epsilon 2 2, whereas this strain state is just pure epsilon 3 3. Okay, and it looks something like this. This should be y, and this is z. So this cube deforms in z direction. Okay. So can we say that this shape or this deformation, these three deformations are pure hydrostatic? We cannot say, because if we see there is a change in shape. The shape is distorted. Initially the shape was cubic, now it is no more cubic. Okay. There is a volume change also, but it is not pure volumetric or pure hydrostatic because shape is also changing. Similarly, this also, the volumetric expansion is happening, but along with that shape of this cube is also changing. Similarly epsilon 3 3. So these three strain tensors, they are not pure hydrostatic, they are hydrostatic plus some deviatory. Okay. And let's talk about this first M1. Okay, that means all three together, which is our M1, this one. Whether this matrix is pure hydrostatic. Okay. So first let's define the volumetric strain. As we know, the volumetric strain is a trace of that matrix. Okay, for this matrix, the volumetric strain is epsilon 1 1. I mean, it is a summation of all diagonal components, epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. Now, if we see this, let's try to understand whether this strain tensor is pure hydrostatic or not. Okay. Let's take epsilon 1 1 is zero point 0.5, epsilon 2 2 is zero point 0.5, and let's say epsilon 3 3 is 1. Okay, so if I draw this, try to understand this visually. Say this is x, y, and z. So if we say like epsilon 1 is zero point 0.5, if it is a 1 by 1 by 1 cube, okay, so this side will have zero point 0.5. Okay, it is a 50% strain, so we can say it is displaced by or deformed by 0.5 in x direction, whereas in y direction similarly, okay, the length of cube in y direction will be 1.5, and length of cube in z direction it is 1, so it will become 2. Okay, so this was 1, now total is 2 mm. Okay, so now we can see that the cube deformation, it will be, if I combine all these three, earlier it was 1 by 1 by 1 mm. With this we can say this will be 1.5 y direction, x will be 1.5, so this is 1 by 1 mm, which will become 1.5 by 1.5, whereas z direction will be 2 mm. Okay, so this is 2 mm. So now we can see this under this strain tensor, the volume change is happening, but along with that the change in shape is also happening. That means earlier it was 1 by 1 by 1 cube, now it's 1 by 1.5 by 1.5 by 2 cube. Okay, that means shape, it is no more retaining its shape, that is cube. Okay, so this is volumetric change plus shape change or distortion of shape. Therefore, we can say for given value of epsilon 1 1 2 2 and 3 3, okay, if for arbitrary strain values, it may not be a pure volumetric. It is a combination of volumetric or pure hydrostatic and deviatory. Okay, so this is not pure hydrostatic. So we will say here it is not pure hydrostatic. So for M1 to become pure hydrostatic, what is the condition? Okay, so let's see that. If we say, if we take the same example here, okay, now let's take epsilon 1 1 is 1.5, epsilon 2 2 is zero point 0.5, and epsilon 3 3 is also zero point 0.5. Okay, so earlier the undeformed shape was 1 by 1 by 1 cube, will become this is 1 by 1 by 1 will become 1.5 by 1.5 by 1.5. So now with this condition we can say this is a volumetric change, okay, plus no shape change, okay, no shape change, because the cube is retaining its shape, that is cube, okay, after deformation. So we can say when all three components of diagonal components of strain matrix are equal, we can say it's a pure hydrostatic. So now this is pure hydrostatic. Therefore, we can say to have a pure hydrostatic, the given matrix or strain tensor to be a pure hydrostatic, these are the two conditions. The condition one is epsilon ij, where I equal to j. That means diagonal component of that strain tensor are equal, okay, and off diagonal components are zero, obviously, right? If for this given strain, okay, if we say epsilon 1 2 is some value, some change in angle, so this deformation will be something like this. There is a volume change, but there is a distortion of shape as well, okay? You can visualize this. Not this way. Okay, so if on top of this strain, if I add epsilon 1 to the uh, and the shape is distorting, okay. So that means off diagonal components, that is strain components, shear strain components should be zero. So these are two conditions: diagonal components should be equal and off diagonal components should be zero, okay? So our answer for this pure hydrostatic, so we can say no, this is not pure hydrostatic. So this is hydrostatic plus deviatoric, because we cannot say epsilon 1 1 2 2 and 3 3 all three are equal. Now let's talk about M2 matrix. Okay. So this is M2, okay, where all shear components are given. So whether this is pure deviatory, uh, so we know the volumetric strain is trace of that matrix, which is 0 plus 0 plus 0 is 0. So we can say this is pure deviatory, right? Because the volume change is 0. So what is the condition for pure deviatory? The first condition is that all diagonal components are 0. Epsilon ij, I equal to j should be 0. Okay. Not only that, if even if they are not 0, okay, the summation of the diagonal component should be 0. That is G1. J1. We know J1 is first strain invariant. Okay. We will see this in hyperelastic. Similarly, like we have seen stress invariant, similarly strain invariant, which is equal to trace of matrix, which is nothing but volumetric strain. Okay. So if the diagonal components are present, but the summation of them is 0, that is J1 equal to 0, that means volumetric strain is 0. So volumetric strain is nothing but J1 only. So we can take again this some example and try to understand. Uh, so let's take 0.5. Let's take this value as zero point 0.2, epsilon 1 1 2, epsilon 1 3 is zero point 0.3, epsilon 1 2 is epsilon 2 1, and epsilon 1 3, let's take zero point 0.1. Okay, and these components are 0 0 0 0. So this is a pure deviatoric. We can see there is no volumetric strain here. But if we say if they are non-zero, but let's say this is zero point 0.3, this is zero point 0.3, and let's say this is minus zero point 0.6. Okay, now here the volumetric strain, okay, is equal to 0.3 plus 0.3 minus zero point 0.6, which is 0. Okay. So we can say even if they are not 0, okay, but the summation is 0, that means it is a pure deviatory. So this is also pure deviatory, because like in x and y whatever expansion is happening, okay, that is being compensated in z direction by negative expansion. Okay, so we can say the volumetric change is 0 in this case, so that way it will become pure deviatory. So now we understood what is a pure hydrostatic. I will repeat. Pure hydrostatic means the diagonal components are equal, okay, and off diagonal components are 0, whereas deviatoric is the diagonal components, the summation of diagonal component should be 0. That is our condition. So I'll come to the first slide where we were decomposed in this way, okay, diagonal and off diagonal components, and our question was whether this is pure hydrostatic and whether this is pure deviatoric or not. Okay. So let's know come to that, and our question answer to that is no, the first one, this m1, and this is m2. The m1 is not pure hydrostatic, it is hydrostatic plus deviatory because diagonal components are not equal, whereas m2 is pure deviatory, okay, because the volumetric strain is 0 here. Now we want to, as we said, we want to split in, our objective is to split strain tensor into hydrostatic plus deviatory. So this one is okay, it is pure deviatory, okay, but we have to further split M1, okay, because it is hydrostatic plus deviatory. Okay. So let's talk about M1 again. Let's split M1 something like this, okay, where what we are doing, the epsilon V is epsilon 11 plus epsilon 22 plus epsilon 33, which is trace of this matrix. So if I split something like this where one third of epsilon V and this matrix, obviously epsilon 11 minus one third of E epsilon V, okay, when we combine them we get this matrix, okay. If I combine these two matrix I get this, because uh, one third of epsilon V plus epsilon 11 minus one third of epsilon V. So this gets cancelled. Okay, we get epsilon 11. Similarly, this component as well. Okay. So now if we split M1 something like this, whether can we say now this, let's give this one M1.1 and M1.2. Okay. Now this matrix we can say it is pure hydrostatic. Remember the condition for hydrostatic, all diagonal components should be equal, which is okay. So this we can say it is pure hydrostatic, and this we can say it is pure deviatory, because we know the condition for pure deviatory, the volumetric strain should be 0. So if I combine these three components, diagonal components, and sum it up, okay, we can say this is, in this case the volume change is 0. So now m1 I have split into m1.1 m1.2 such that now hydrostatic plus deviatoric now split into pure hydrostatic and pure deviatoric. Okay, now so I could say this is my strain tensor, okay, which can be split into three matrices. The m1 is this one, plus this M2. Okay, so first one is pure hydrostatic, this one is pure deviatoric, and this one is pure deviatoric. So I have three strain tensor, but I can combine this M1.2 and M2 because both are pure deviatoric. If I combine them, it is also pure deviatoric. So I can write the decomposition of strain tensor. This is a final one. Okay, this M1.1, which is this. Okay, epsilon V, one third of epsilon V, can also we can say one third of trace of that matrix. Okay, this matrix. Okay, I will just say trace of epsilon ij is equal to epsilon 11 plus epsilon 22 plus epsilon 33. So this is my pure hydrostatic, and this M1.2 and M2 together is pure deviatory. Okay, so this is my pure deviatory. So my objective is achieved. So based on this, we will see the decomposition of stress tensor in next lecture.